Hello everyone, welcome to lecture number 56 of the NPTEL course on Riemannian geometry. So last time I stated the uniformization theorem for space forms. So space form remember is just a complete Riemannian manifold with constant sectional curvature. So I stated the uniformization theorem. The next 3 lectures will be occupied by the proof of the uniformization theorem. Towards the end of the previous lecture, I proved the following, that suppose we have the model space with sectional curvature constant kappa, then the metric in polar coordinates has this very explicit form, right. So the aim of this particular lecture is to prove a similar formula in all space forms, okay. So that involves what are called as Jacobi field computations in space forms. So that will be the main topic for this lecture. Okay, so here's the main proposition that we'll prove. So let MNG be a space form with sectional curvature identically kappa. Let gamma be a unit speed geodesic okay, and let J be a so let J be a normal Jacobi field that so this space J perp with a subscript 0 will basically denote the space of all normal Jacobi fields that vanish at the initial point. So let us say J is one such Jacobi field, then we have the following formula. J of t is given by this generalized sine function times E of t, where E of t is a parallel normal vector field along gamma, i.e. that just means that E prime of t is identically 0 and E is perpendicular to gamma dot for all t, okay. So all the Jacobi fields are basically given by multiplying these normal parallel vector fields by this generalized sine function, okay. So what is the proof of this? So first remember, long time ago when we proved this this fact that the sectional curvature actually determines the curvature tensor, as a consequence of that we had made the following observation, that if the sectional curvature is a constant kappa, then its curvature tensor is given by this explicit formula. Okay, if you want an actual reference, I think it was in lecture 24, right. So then I mean this is for the curvature 40 tensor or 04 tensor. What about the curvature endomorphism? So then R of xy applied to z will clearly be given by xw, the inner product of xw acting on y minus the inner the it will be the inner product of yz acting on x minus the inner product of xz times y, okay. So now let us look at our Jacobi field. So let J be a normal Jacobi field, then by the Jacobi field equations we have by the Jacobi equation we have that this is 0, but by our calculation of the curvature tensor this is precisely sorry I should there should be a kappa in front of this, right. Okay, so this is going to be kappa times gamma dot times j minus j gamma dot times gamma dot. But because j is orthogonal this is 0, and because gamma is unit speed this is equal to 1. Okay. So we get that j double prime plus kappa times j is 0. Okay. So now suppose j were given in that form, okay, where E is parallel and orthogonal, then what is j double prime plus kappa times j? Well, that is precisely because no derivative will hit E since since E is a parallel vector field. So this is precisely going to be the generalized sine function differentiated twice plus kappa times the generalized sine function times E. Okay. But when I defined the generalized sine function I observed that it is actually I mean it is a solution to this ODE that this is actually 0. So you get that this is 0. Okay, so I should have said that right. So then by our earlier observation any Jacobi field, any field that is given by this formula is actually an orthogonal Jacobi field which vanishes at gamma. So now we just consider the space of all such vector fields. So let J tilde be the space of all orthogonal Jacobi fields which are given in this form. For some choice of E. Then my claim is that the dimension, this forms a subspace clearly of the space of all Jacobi fields, orthogonal Jacobi fields that vanish at the initial point. My claim is that this is n minus 1, the dimension of this space. Assuming this, then we are done, because we already know that the space of all orthogonal Jacobi fields, firstly the space of all right orthogonal Jacobi fields that vanish at 0 is n minus 1 dimensional. Why? Because a Jacobi field is specified by the value at 0 and the derivative at 0. The value at 0 is 0. The derivative at 0 has only n minus 1 dimension worth of choices. Why? Because you can't have the derivative pointing in the direction of the velocity vector, otherwise your Jacobi field will not be orthogonal, right. So the derivative points your j naught j prime 0 has to be perpendicular to the velocity vector, that just leaves n minus 1 dimension worth of choices. Okay. But then you already have a subspace which is n minus 1 dimensional, so this implies that that subspace has to be the full space. So that implies that all Jacobi fields are actually given by things that look like this, and that completes the proof of the proposition. Okay, so what is the proof of the claim? Okay, so so to prove the claim, I notice that firstly, I mean J is completely determined by E of t. So as soon as you determine E of t, you are done. Okay. But on the other hand, E of t being a parallel vector field, because parallel transport exists for all time and is unique, E of t is actually determined completely by E of 0, right. But how many choices for E of 0 do we have? Well, E of 0 ought to be perpendicular to gamma dot of 0. So that gives n minus 1 dimensional worth of choices. So this implies that the dimension of the space is actually n minus 1 and we are done. Okay. Alright, so now we know exactly what form all the Jacobi fields take. So here is the key sort of consequence of that. So let Mng be a space form with sectional curvature identically constant kappa. Let P be any arbitrary point and let U be a geodesic normal neighborhood with coordinates with geodesic normal coordinates centered at P. Then the metric restricted to this geodesic normal neighborhood exactly has the form of our model matrix, okay, where as before R of x is the Euclidean distance, which we know is also in fact the distance from the point P, okay, and this is the usual Euclidean metric, Euclidean round metric or the induced round metric on Sn minus 1 in these coordinates. So this is basically the set where R is equal to 1, okay. So in particular this implies that UG is isometric to a geodesic normal neighborhood So maybe I will use a different notation because this UK was something I had defined earlier. So maybe I will say that it's isometric to a geodesic normal neighborhood. This WK may in general be smaller than the UK that I had from the previous lecture, right. Okay, so let us prove this proposition. So firstly by Gauss lemma, the metric already has the form dr squared plus hr because the radial vector field is orthogonal to these geodesic spheres. So where hr is the induced metric on on this geodesic sphere. Okay. So now let x be a tangent vector to that sphere. For concreteness, let q be the exponential p of r theta, where theta is some unit tangent vector, right. And suppose in my normal coordinates, suppose x is given by this, okay. Then our goal is to actually calculate what right. So let me call the tangent vector at q as xq. So our goal is to actually calculate what this is, okay, because that will basically be HR of I mean this will be HR of xq comma xq, okay. All right. So my claim is in fact the following. So the claim is that that this norm squared is precisely this. Okay, where this is precisely the Euclidean norm square in these normal coordinates. So that just means the sum of squares of the components of x. And then note that by the polar coordinate formula for the metric on Rn, clearly this divided by r squared is basically the if you identify the sphere with actually the unit sphere, then this is precisely the norm squared with respect to the metric on the unit sphere, okay. So this would imply that this is this times okay, and we will be done. That's what we wanted to prove, okay. So let's prove the claim. Okay, so consider the following vector field. So we define a vector field x on all of this geodesic normal neighborhood. So the value at little x is going to be, you keep the coefficients as these you keep the components the same as the components of xq, but now this is del I at the point x, okay. So basically the idea is that you have a certain vector at q, you just extend that so that the components remain constant, okay. And let J be the Jacobi field such that J of 0 is 0 and J prime of 0 is precisely the vector field xp by R, okay. So then in normal coordinates we know exactly what the Jacobi field looks like. In normal coordinates, this Jacobi field is going to basically look like t times the components of x by r times del I at gamma of t, okay. So, in particular, right, J of r is precisely this vector field xq, right, which we know is perpendicular to gamma dot at that point. Okay, which means that J is a Jacobi field that is orthogonal to the velocity vector at 0 and at r. So, by a lemma that we had proved previously, this implies that J is a normal Jacobi field, and in fact because it vanishes at the origin, it is actually in this space. Okay. So, then by the proposition we can also write J of t as this generalized sine function times E of t, where E is some parallel vector field which is orthogonal to gamma dot. Okay. So, now let us compute. Okay. So, so I want to compute what this is, but by our observation in the previous slide, this is precisely the value of the Jacobi field at J of r, the norm squared of that, right. But then because this is given in terms of this parallel vector field, this is just sine k squared of r times this. Now, parallel transport does not change the norm, right. So, so this is the same as the norm of E at 0, but at 0, because we are using geodesic normal coordinates, the metric G is just the Euclidean metric. Okay. But what is next note that E of 0 is precisely J prime of 0. Okay. So, that is just a simple calculation. So, I mean you just differentiate this to see that J prime is given by the generalized cost function, I mean is basically given by the derivative of the generalized sine function times E. The derivative of the generalized sine function at 0 is 1. Okay. So that proves this. So, putting it back into our earlier calculation, so continuing our earlier calculation, this will now be this times the norm of this with respect to the norm squared with respect to the Euclidean metric. But what is J prime of 0? Well, you go to the previous slide. By our choice, J prime at 0 was basically given by this. Okay. And xp has the same components as the components of xq. Okay. So this is the same as but this is the same as the norm squared of xq in Euclidean metric. Okay. So that proves the claim. And hence the corollary. Okay. All right. So, so now we have basically shown that on any space form you can find a geodesic normal neighborhood that's so that the metric restricted to that is isometric to a geodesic normal neighborhood in the model space. So now the point is you want to somehow globalize this, right, move from local isometry to a global isometry. So that is what we will so there is another sort of key ingredient before we can prove the uniformization theorem, and that is namely a generalization of this no conjugate point lemma that we had in the proof of the Karta Hadamard theorem. Okay. So, that will be the main focus of the next lecture. Alright, so that is it for now. Thanks for your attention, and I will see you in the next lecture. Thanks.
Hello, sir, can you repeat the last sentence?
Oh.
Because we have to show the faculty in the end of the lecture.
Oh.
Just you can repeat the last sentence and I will
Okay.
see you in the next lecture.
Alright, so this proves the claim. So far we have shown that given any space form, if you look at a geodesic normal neighborhood, then that is isometric to a corresponding neighborhood in the model space. So somehow we need to globalize this, move from local isometry to global isometry. So there is another sort of key ingredient in that, and that is namely the a generalization of this no conjugate points lemma that we had in our proof of the Karta-Hadamard theorem. So that will be the focus of the next lecture, and then in the subsequent lecture I will complete the proof of the uniformization theorem. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next time around. Thanks.